It's good. Okay, awesome. So thanks everyone for joining us in person and on Zoom. I'm really excited today to introduce Stacie Bauman, who's going to be talking about a proof of the NKT conjectures. So take it away.
Yeah, hello. Thanks again for inviting me. I'm Stacie. I'm a grad student at Auburn University. And today I'm going to talk to you about a proof of the NKT conjectures. And this is all joint work with Joseph Briggs, another professor here at Auburn. All right, so first I'm going to start with some definitions. So what is an NKT graph? So an NKT graph is a graph on n vertices in which every induced subgraph on k vertices contains a clique on t vertices. So here, but down below, right, I have a 5, 3, 2 graph, right? There's 5 vertices. And if I pick any 3, so say I pick these 3, and I look at the induced subgraph, then there contains a K2. So right, to double check this is a 5, 3, 2 graph, right? I'd have to check every single set of 3 vertices and make sure there's a K2. But in this case, up to isomorphism, I just checked the 2 cases of 3 vertices. So this is a 5, 3, 2 graph. So again, you have to have 5 vertices. Every single set of 3 vertices has to contain a clique on 2 vertices. Okay, let's do another example to make sure we got it, right? So this is a 9, 7, 3 graph. So instead of checking all the cases, let me just kind of argue through this one, right? The worst thing that we could happen is that we have these 3 isolated vertices in our set, but then we have to have at least 4 from this complete component over on the right here. So that definitely, when I look at the induced subgraph, contains a K3. And right, I've given this talk before, and someone said, okay, well, isn't that also a 9, 7, 4 graph? Yes, it is. So yeah, this is definitely also a 9, 7, 4 graph. So any 9, 7 T graph, any number smaller than T would also be one of those graphs, right? Okay, so let's look at one non-example now. One more example here. So this one is not a 9, 7, 3 graph. Remember, there just has to be one example of 7 vertices that doesn't contain a K3. So in this case, this set that I had here does not contain a K3. So this one would not be a 9, 7, 3 graph. Now, even though some of those sets of 7 vertices would contain the K3, there just has to be one to make it not a 9, 7, 3 graph. Are there any questions about the definition? Okay, and I will say, feel free to jump in and ask questions as I go if you want. Okay, so now kind of an extremal question, right? We're gonna look for minimum NKT graphs. So this is the NKT graph with the minimum number of edges among all NKT graphs. So which one has the minimum number of edges? Okay, so maybe since you're in person, this might actually work a second. So I want everyone to maybe think for a second through some of these cases and see if we can come up with the minimum NKT graph. So I'll give you like a minute or two. But I think if I gave you longer, maybe we could come up with most of these. So maybe think through, and I know there's some people in person, if you want to like talk to your neighbor, talk to your neighbor.
NK1 is just a empty graph. Graph? Yeah. It's a complete graph. Complete graph. And then
complete with isolated.
Yeah.
And the last one should be no independent set or something.
No independent. So it's
Yeah.
Yeah, so I'm hearing very correct things. Maybe that last one is the hardest one, right? So yeah, these ones maybe you can kind of come up with, right? So NKT or NK1, right, is just the graph on n vertices on the empty graph, right? So just for the future, in case you're unfamiliar with the notation, right, I'm gonna write this as NK1. That just means n copies of K1. K equals T, right? Any single set of K vertices I pick has to have a complete graph on K vertices. So that would have to be the complete graph on n vertices. Yep. When n, okay, right, I just need every single set on vertices to have a KT. So the minimum one would be 1 KT and then a bunch of isolated vertices. And then finally, I kind of heard this Turon mentioned when I was listening in, right? So yeah, this last one is Turon's theorem. So up top is the statement of Turon's theorem, and maybe it's the complement of what you normally kind of think of when you think of Turon's theorem. But it says that the unigraph on n vertices without an independent set of size r, with a minimum number of edges, is the disjoint union of r minus 1 cliques, where the number in vertices in each clique differs by at most 1. So exactly an NK2 graph, right, is just a graph without an independent set of size k, right? Because if I need every k set to contain a k2, that's just an edge, right? So we don't want an independent set of size k. So it's exactly Turon's theorem here. So right, here's an example, right? The unique minimum 10, 4, 2 graph is this disjoint union of cliques. So what I mean by that is every component's a clique. And the size of the cliques, the number of vertices differ by at most 1. So here you can double check that, right? This is a 10 vertices. There's 3 cliques, right? 1 less than k. And we make them as balanced as possible. All right, any questions about those 4 examples? Okay, so that kind of leads to this conjecture due to Hoffman, Johnson, and McDonald in 2015. So they had these 2 conjectures. So the first one, the weak conjecture, is that every minimum NKT graph, or there exists a minimum NKT graph that is a disjoint union of cliques. And the strong one is that they're all disjoint union of cliques. And we're going to prove that strong one. So going back to those examples real quick, let's just double check, right? All of these, including just an isolated vertice, counting that as K1, right? These are all disjoint union of cliques for all these examples we just did when we were thinking about them. That was kind of the conjecture in general. And there was a little bit of history done, right? Or a little bit of progress made towards this conjecture before we came along. So in 2015, Hoffman, Johnson, and McDonald, like I said on the previous slide, they kind of stated the theorem or the conjectures, and they showed kind of the structure of what these minimum disjoint union of cliques graphs are. So they said, if the theorem is true, then these graphs have this structure. And then in 2017, the same group plus Noble, they proved the strong conjecture for t less than or equal to, or k less than or equal to 2t minus 2. And I'll say we use a different kind of method than them. Their method was kind of restricted to those small cases of k. Okay, so once this conjecture was stated, there was kind of a little bit of skepticism because of this kind of fact here. So all minimum NKT graphs are not unique. So here are 2 examples. They are both the minimum 653 graphs, but they're different. But if you notice, they are still both disjoint union of cliques. So, with a little bit of argument, you could show that these are minimum 653 graphs, but I just want to point out, right, they both have 6 edges. They're both minimum 653 graphs, and they have this different structure. So this was kind of leading people to believe maybe this conjecture wasn't true. It's kind of strange, right? In Turon's theorem says the unique minimum graph is this disjoint union of cliques. There's only one of them. But if this conjecture was true, right, there's going to be more than one minimum, which was kind of strange. And actually, Hoffman and Pavlich showed that for any integer n, you can find some k, n, and k such that we have n isomorphic or non-isomorphic minimums. So you can get as many of these minimums as you want. So not just 2 in the previous slide, you can get a bunch. Okay, so on the next slide, I'm going to talk about what kind of these are our worries about this. But first, I just want to point out this observation. If a graph is a disjoint union of cliques, then the independence number is equal to the number of components. So right, if I was trying to find an independent set and I have a disjoint union of cliques, right, I could only pick at most 1 vertex from each component. So here's a quick observation. This is going to come up a few times later in the presentation. But looking at those 2 examples we just saw, right, independence number 2 and component, there's 2 components, and same with this one has independence number 3 and 3 components. Okay, so this observation, and although I called the last one an observation, I think it was kind of easy to see. This one would actually require a proof that I'm going to skip. But this observation kind of put our worries to ease about that kind of multiple minimums situation. So what we showed was if there are more than one of those minimum NKT graphs, then their independence numbers are different. And this actually kind of inspired the proof as well, which we'll kind of go through a little bit. So again, back to those minimum 6, 5, 3 graphs. There they two are, and right, they both have a different independence number. So we kind of saw that when you have these multiple minimums, you get different independence numbers for each graph. Okay, so again, we, in our paper, right, we proved the strong NKT conjecture, and that proves the weak one. And so today, what I want to do is go through an example that'll kind of show you how the proof goes. So I'm not going to prove it in general for you today, but we'll go through how to prove that the minimum 10, 8, 3 graph is a disjoint. Okay, so how I'm going to do that, again, I kind of said, right, the independence number being different kind of drove this proof. So what I'm going to do is I'm going to show what the unique graph on the minimum number of edges, 10, 8, 3 graph on the minimum number of edges with a specific independence number is. So I'm going to fix the independence number, figure out what the minimum graph is. I'm going to show that these are all disjoint union of cliques. So if every single one for every independence number is a disjoint union of cliques, then definitely the minimums overall are also disjoint union of cliques. So let's go through that, right? So again, let's start with independence number 1, A equals 1. And the only graph with independence number 1, right, is the complete graph on 10 vertices. And that is a 10, 8, 3 graph, right? So yay, easy example, right? Or easy first case, right? The minimum NK or 10, 8, 3 graph with independence number 1 is K10. Okay, so what about independence number 2? Again, we can just use Theorem's theorem. The minimum graph in general, if we're ignoring the 10, 8, 3 graph component or the 10, 8, 3 requirement, the minimum graph with independence number 2 is K5 plus K5. And that just so happens to still be a 10, 8, 3 graph, right? This is pigeonhole, right? If I take any 8 vertices here, at least 3 of them are from the same component, and that's a 10, 8, 3 graph. Okay, so it's seeming like I'm just applying Theorem's theorem here so far, right? So same with this one, right? Minimum graph with independence number 3, ignoring the 10, 8, 3 condition is K3 plus K3 plus K4. And that just so happens to already be a 10, 8, 3 graph. Again, pigeonhole, if I pick any 8 vertices, at least 3 of them are in the same component. All right, so let's try to do that when we get to independence number 4. So when I get to independence number 4, the minimum graph by Theorem's theorem is this graph, right? K2 plus K2 plus K3 plus K3. But this case, this isn't a 10, 8, 3 graph. So we have to do something else, right? So this isn't a 10, 8, 3 graph, right? Here's a set of 8 vertices that don't have a K3, don't have a clique on 3 vertices. Okay, so we need a new strategy when we get to independence number 4. Okay, so what I'm gonna do is I'm going to construct a 10, 8, 3 graph G that has the minimum number of edges. So kind of prove the weak with independence number 4. I'm going to prove the weak conjecture first. And then I'm going to argue that this is the only one, there's no other examples. Okay, so what I'm going to do, right, if I have independence number 4, there's an independence number or set of size 4. So I'm going to consider that S, kind of consider that separate in the bottom G minus S. Okay, so I claim that what's left over has to be a 6, 4, 2 graph. So why? Let's go through that. Right, so if this whole thing is a 10, 8, 3 graph, then I can pick, if I pick any 8 vertices, there has to be, so At worst, right, I could pick 4 of those kind of vertices from the independent set. And each of those vertices, only one of them can be in my K3, right? Because they're an independent set, right? So this is kind of the worst case scenario, right? If I pick 8 vertices, at most 4 of them are in there. There's got to be 4 more in the bottom. And I have this K3. But then if I kind of ignore that independent set of size S, right? That means there has to be a K2 down here. So that means this gray space down here needs to be a 6, 4, 2 graph. There's 6 vertices. Any 4 I choose has to have a K2 somewhere. So I'll pause there. Are there any questions about that argument? Sometimes that one gets a question. All right. So if this bottom part has to be some 6, 4, 2 graph, then there's a unique minimum 6, 4, 2 graph, right? This is Theorem's theorem, right? The t equals 2 is always Theorem's theorem. So here's the unique minimum 6, 4, 2 graph. And I also claim that there has to be an edge up from each of these vertices up to my set S. Because if there wasn't an edge up from one of these vertices, then I would have a larger independent set, right? If there was no edge up from this one, right, I could take my 4 vertices up here and this one, and I'd have a larger independent set. Okay, so I know my G minus S down here looks like this, right? So I'm just showing that there has to exist one with the minimum. So there at least has to be this many edges, right? So let's define G to be this graph, right? K1 plus K3 plus K3 plus K3. And right, that's a disjoint union of cliques. And we just talked about you had to have at least that many edges, so this one has the minimum number of edges. Okay, so that's the weak conjecture part. But now I want to show those are the only such cases. And I will say in general, we're kind of doing this specific example. I applied Theorem's theorem. In general, that's an induction on T step. So T equals 2, that's the minimum, right? I can do induction on T in that case in general. Okay, so to prove the strong part of the conjecture, right? I still know I have to have something right like this, right? Because the K2 plus K2 plus K2 in the bottom was the unique minimum, and I have to have edges up. So if I do have another one, it still looks like this. Okay, so what if instead of having my K1 plus K3 plus K3 plus K3, I have 2 vertices in different components adjacent to the same component in S. So why is this one a problem, right? This is a problem because then I have an independent set of size greater than 4. If I pick these pink vertices, remember these are the only edges if I have another minimum. If I pick these pink vertices, there's an independent set bigger than 4. So I know now that edges in different components can't go to the same component in S. Okay, what about the other case? So now what if 2 vertices in the same component go to different vertices in S prime? Well, by that last fact, right, these ones can't go to the same ones that they just went to. So you have to have a graph that looks like this. And right, this is not a 10, 8, 3 graph. Here's a set of 8 vertices that don't induce a K3. So in general, I kind of picked a nice case for this last little step. This gets a little trickier in general, but with this nice small numbers, that works out pretty good. Okay, so for independence number 4, we just showed that K1 plus 3K3 is the minimum graph, right? All right, and I'll save the time, right? For A equals 5 and A equals 6, those are pretty similar to the A equals 4 case. So you can do the same idea there with the independent set of size S, and you get those cases. And then for independence number 7 or bigger, that's not possible. So if you have independence number 7, right, you could pick one other vertex. There's 8 vertices, and if there's an independent set of size 7, there's definitely not a K3. So anything bigger than 7 is just not possible. Okay, so that proves it for this example, right? If we fix the independence number and show that the minimum is a disjoint union of cliques, then the minimum overall has to be a disjoint union of cliques. So you might ask, right, well, which ones are actually the minimum, right? We just found all these minimums for each independence number. So you could count the number of edges and figure out which ones are actually the minimum. So here, right, if I count all the edges of these, I actually get 2 minimums, like we were kind of talking about earlier in the presentation, right? Both independence number 4 and independence 5 give 9 edges. So both of these graphs here are the minimum 10, 8, 3 graphs. So again, that was just one example with specific numbers, but we proved that for any n, k, and t. And we kind of used that similar strategy of breaking it up by independence number. Again, that came from the fact that we realized that all of those minimum graphs had different independence numbers. And we kind of used that strategy to prove the main theorem. And I do also want to mention, right, so another group came along and they showed the precise structure of these minimum NKT graphs. So they did it at the same time we were working, right? So they were saying, if the conjecture is true, this is what the graphs look like. But now we can combine both of our results and answer this question, right? What is the exact minimum number of edges in an NKT graph? So our result says it's a disjoint union of cliques. Their result says if it's a disjoint union of cliques, it has this structure where it's a bunch of isolated vertices and then these kind of balanced complete components on the right here. Right, so basically what they did is they took this table and they were able to say, okay, which ones actually are the minimum? Our proof just says the table exists, right? One has to be a disjoint union, one of those minimum, or all of those minimums have to be a disjoint union of cliques. And one cool thing we kind of like about this theorem, right, is it is an exact result, right? It's not asymptotic, it's not approximate. All right, so what could we do next, right? So I have a couple future directions that we could possibly go in, right? So first one is instead of considering the minimum number of edges, we could consider the number of cliques on S vertices, right? So this S in our example was 2, right? Because we were considering the number of edges, that would be K2. So this has actually been looked at a little bit. So if you fix T to be 2, this is kind of one way you could kind of extend Theron's theorem. So this has been looked at a little bit. Erdos actually conjectured that it was a disjoint union of cliques would be best back in, I think, the 60s. And then Nikorov disproved this conjecture, and he showed that a clique blowup of C5 has independence number 2. So it's an N3-2 graph, but it has fewer cliques on 4 vertices than that kind of the disjoint union of cliques graph that has the minimum number of K4s. So it was there was this conjecture that it might be a disjoint union of cliques, but that was actually disproven, which is interesting. And there are some results for this, and it uses flag algebras, which I am no expert on. I think probably more people in that room could tell you about that than I could. I know some of you are very familiar with flag algebras. Okay, so yeah, so there's some asymptotic results about some of these very small cases. So they did, I think, cliques on like 3 through 7 vertices, they have asymptotic results on using flag algebras. So maybe kind of looking at this in the future, coming back to it, it was a few years ago, so maybe you could come back and kind of do some results about this. Also, maybe kind of trying to look at different values of t. Maybe for some reason we can get some results about that we can't get when t equals 2. So that's one future direction. The next, there's this result that kind of, again, strengthens Theron's theorem. And it says that if a graph is kind of similar or has a similar number of vertices to the minimum graph, so if there's only a few more edges, than the minimum graph, that the structure is pretty similar. So here's kind of the version for Theron's theorem, right? I'm not going to read it all, but you can read it, right? It basically says that if you have a few more edges than whatever the minimum number of edges is, if you add that many edges or some function in that value, you can eventually get that structure. So we think that maybe we could prove something similar with our main theorem, right? So kind of a very similar kind of theorem here to those. Another future direction is looking at inclusive minimum NKT graphs. So that is the NKT graph, which if you remove any edge is no longer NKT. And so the first question you might ask, right, is every inclusive minimum NKT graph necessarily a disjoint union of cliques? And there is a counterexample to that, right? If you look at C5, this is a 5-3-2 graph. I think that was my very first example, right? But it doesn't contain the inclusive minimum 5-3-2 graphs that are disjoint union of cliques. So it doesn't contain these disjoint union of cliques, right? But it's still inclusive minimum, right? If I remove an edge, it's no longer 5-3-2. So a question could be to ask, among all inclusive minimum NKT graphs, what's the maximum number of possible edges? So when t equals 2, this is done, but we kind of conjecture that maybe this maximum is still achieved by the disjoint union of cliques. So not all inclusive minimum NKT graphs are disjoint union of cliques, but maybe the ones with the maximum number of edges are. And then finally, maybe two more general, more future directions is you could consider the bipartite version of this question. So that's kind of listed above, but basically the same exact thing with bipartite graphs. Now, I think this might be a little difficult, right? Because instead of the smallest case being done, like Theron's theorem in the complete case, right? The smallest case maybe is there's Zerankovich open problems, right? So maybe it's hard, but it could be something to look at. And then the final future action, I think I've given this talk a few times and everyone always asks me this one. So I put it in here this time. Instead of considering the complete graph on T vertices, right, you could pick any graph you want on T vertices, right? So you could define a graph as NK, H, and say every graph on N vertices in which every set of K vertices induces some copy of H. So we could do that. But that's all I have. I can go back to these if anyone wants them, but thanks.
Let's thank Stacie. Any questions for our speaker? And if you're online, feel free to unmute yourself. But first we have Brian.
Okay. Hi, Stacie. It's very
Hi.
nice.
Okay.
I have another future direction for you. You have a lot.
Oh, cool.
But I was thinking through the whole thing, and I was wondering if you replaced the T with a graph of chromatic number at least T. And in particular, the first interesting case there would be T equals 3. So you would have an odd cycle. So in every K set of K vertices, you would have to have an odd cycle.
Okay, yeah, I think that would be interesting.
I'm thinking Erdős stone along that.
That's what I was thinking. I'm wondering, yes. Yeah, I think that would be interesting to look at. Yeah.
Can you do something with oriented graphs? Right. Say you would like maybe some triangles that have particular, there's two triangles that have orientations, so you could try to ask.
So yeah, did you hear that, Stacie?
Kind of.
He's
did you
asking
say
about
oriented graphs?
Yeah, so your base graph, your n vertex graphs are oriented graphs, and you choose k vertices, and you want the presence of something. In this case, it would be you were thinking of all kinds of oriented triangles.
Yeah, you can say this kind of maybe. Yeah, you can have this. You maybe need the transitive triangle because you can have full tournament that is.
Yeah, you can avoid any non-transitive triangle by starting with the transitive triangle.
So you need you will get transitive.
Yeah, transitive would be the natural thing to ask in that case.
Yeah, that's interesting. So you could say avoiding some kind of structure or containing some kind of structure.
Be avoiding, right? Well, no.
Yeah.
I don't know what minimum. Well, yeah, minimum so that you have it. But I would think it'd be the same problem, except
now every clique will be a tournament.
Yeah, everything's a tournament.
True.
So I think in that case, so one of the reasons why I was thinking about chromatic numbers, it's an Erdős-Stone type of thing, so regularity helps. You know, you go Turan, and then to go to Erdős-Stone, it's one of the easy applications of the regularity lemma. But also it might not be the same structure because you might have little things that you can add to the disjoint cliques, and it wouldn't be disjoint cliques, which I think, to my mind, would make it interesting because it's not the same, or it could be the same. And that also is somewhat interesting.
Yeah, I think that could be very interesting to look at.
Would you then get some approximate result, like it is within epsilon edit distance from this joint union of cliques?
I would assume yes that it's the that there is an approximate version where the structure the regularity graph should be disjoint cliques. You should be able to do that for the case that I was talking about. You apply the regularity lemma, you apply your theorem to the reduced graph for triangles. And then you're close. You know that your graph has to be close to your extreme disjoint cliques. And now you have to see whether there's a way to get around it.
More, yeah.
And I guess you could go to hypergraphs here too, right? You really
yes, someone, I have given this talk or a similar talk before, and someone mentioned going to hypergraphs, and there's a Turan's equivalent in hypergraphs. So yeah.
Yeah.
Well, if you want harder, go to posets. Same question, and vertex poset, you choose vertices, and you want to the existence of a chain. I don't know that it would be different. It's probably the same. Start with disjoint chains.
Any other questions?
No online questions.
Yeah, no online questions, I guess. Okay, awesome. Then let's all unmute everyone on Zoom and let's thank Stacie one more time.
Yeah.